let's get going. So last time and the time before, and for quite some time, we've been talking about PCA. But last time we talked about it for visualization. And basically, the idea is we run PCA. We get a couple of embeddings Z. We use a couple of dimensions for our. We use a couple of the principal components. I'm going to start calling them embeddings today for reasons that'll become clear. We take a couple of principal components, get the weightings or embeddings for those for all of our data items X. Then we plot those in some sort of scatter plot, right? We introduce multidimensional scaling, which is a scare quotes crazy idea, which basically says, let's directly optimize the pixel locations of the embeddings. Let's just move the embeddings around directly, kind of like gradient descent on the points in a scatter plot. And we need, in order to do this, at least to set up a cost function to say how good the embeddings are that we learn. So a traditional MDS cost function sums over all pairs of examples, computes a distance, usually into what we call traditional. Again, I'll put this in quotes, computes the distance between the points X in the original D dimensions, compares that and tries to zero it with respect to a distance in a scatter plot, and tries to basically match the distances in the sense by trying to minimize the squared difference between the distances, right? And just to drive this home, we can do this again, right? So we have, MDS tries to take a large distance in the space of X, which generally speaking will be very, very high dimensional, and make it equivalent in the low dimensional Z, which in our case today we'll be talking about 2 dimensions, but is just in general lower dimensional, and small distances between points also still small. Okay, fine. And that means basically we're going to have to warp the space of X. Like we're going to have to put these points down in funny places where there are some violations of the distances, but we want in the like the sum over all pairs sense this to be minimized. So there's going to be some warping going on, and in order to make distances large, we're going to have to throw points way out in some weird sense. There's like, yeah. You can think of this as a non-parametric dimensionality reduction technique, because we literally have embedding points for every single data point. We're not learning a W matrix of parts or principal components or something like that. And we're just trying to make the Z preserve high dimensional distances in X, okay? So if we have a data set like so, this is now all of X, something like this, right? So don't worry about there's an X and an O, you'll see why in just a second. If we use PCA, we do basically PCA finds the axis that of principal variation, then projects all the data points onto that. And this leads to what we'll refer to as a crowding effect or whatever. Like the principal axis of variation is we really would like it to be here, but we have an outlier, so it tilts the principal axis of variation up. We do a projection, we get this crowding kind of effect. That's not great. Basically, PCA points only basically only moves points closer. They just move points closer. MDS. On the other hand, ideally, the idea is that it can preserve distances. In other words, it can actually, if you look at the average distances between these two points in this projection, in this new one-dimensional representation of this two-dimensional data on the left, these average distances are all pretty good. And this point, when you look at its average distance to all of these, well, that's not an unreasonable approximation to its average distance to all of these. And maybe you could have projected this point over on the other side or something like that and get the same kind of behavior, right? So again, we're focusing on the distances and trying to preserve these distances in the all pairs sense, okay? Fine. If we consider a data set like this again is just our data set X. The labels here are just here to help see what happens after we project it. Payment, let's say axis of principal variation, or if we ran PCA on a data set like this, what are we going to get?
I guess it's going to be a line, like a vertical line.
It's going to be, it's actually very difficult to say. This is a data set designed to say exactly what it's going to be, a line like this, or it's going to be a line like this, who knows, right? Or a line like this, doesn't really matter. It's going to be something. We're going to rotate to whatever that is, and it's going to be very sensitive to whatever the noise is, and then we're going to project. And all the circles are going to go here, and the triangles are going to go here, and the x's are going to go here, and the circles are going to go here, and they all kind of get mashed together like this, right? But the local distances, are small between the x's, and they're large between the x's and the triangles, and so on and so forth. So you can imagine that if you were able to actually learn some z's, and like you were able to actually find a good local minima of this cost function, which is non-convex and nasty, you should be able to learn embedding like this, where all the x's are aligned, next to one another, then the triangles and a gap here, and then triangles, and then circles, so on and so forth. Okay, fine. That would be really cool. And I'm going to use a word here that we'll return to later. What we're really kind of thinking about is that there is some manifold on which our data lives, and we'd somehow like to parameterize that manifold such that we can index the data in a way that's both meaningful for scientific discovery, but also useful for classification and regression later on. Obviously, if we were going to build a random tree-based or random forest-based classifier in this space, we'd do a much better job, because all of the classes here are laid out in a way that you can distinguish them easily in this embedding space, in this basis. Okay, so we can't use SVD to compute a solution here. We don't have a closed form solution like we do for PCA with orthogonal bases and unit norm principal components. Instead, we can do gradient descent on the Z values directly, or stochastic gradient on the Z values directly, depending on the size of your data. And what you end up doing is learning a scatter plot that tries to visualize. It's not convex, it's sensitive to initialization. And obviously you can rotate and translate and do all sorts of things to the embedding. And so, yeah, it's super multimodal. Could we use a clustering algorithm that works for non-convex data? Not sure what non-convex data is. So I think, and then the question goes on to say, then we just split the data by cluster and then run PCA. If you mean, and I think you mean not convex data, but if you mean that you have, if the clusters don't correspond to convex regions of data space, right? And you ran some sort of k-nearest neighbors clustering algorithm or something like that, and you were able to extract the clusters, right? So indeed, so yeah, great. If you ran PCA on one of these clusters, you still would not necessarily actually have a good description of this cluster, because you'd learn some axes of variation, and then that's probably not a good description of the data if you want to describe stuff within the cluster. Okay, does that make sense? It'll make more sense when we talk about isomap later, if that's not making sense. We'll get there pretty quickly. The NBS default objective is the square difference of Euclidean norms. So we've got, Euclidean norms here, and then just a square distance that we use to compare the distances. But there's obviously a degree of freedom, many degrees of freedom, but really a big degree of freedom in setting in choosing which distance functions to use here and which distance functions to compute for comparing the distances, right? So this is one choice, this is one choice, and this last function is one choice as well. Okay, so the functions are not necessarily the same. So D1 is a high dimensional distance that we want to match. D2 is a low dimensional distance we can control, and D3 controls how we compare the high-low dimensional distances. So the default objective function, or like the parameterized default objective function, is given by this, one choice is what's referred to as classic MDS, which says that the distance that you compute in X space is just the inner product between Xi and Xj. The distance in Z space is just the inner product between Zi and Zj. And if you read a painful but beautiful paper by Chris Williams at the University of Edinburgh, from, I think it's in the 90s they wrote it, basically you can show that this corresponds to PCA. And this is that means that it's not a useful thing to do really. But if you change the choice of distance functions to, say, for instance, be an L1 norm or something like that, then MDS starts to do interesting things. So here's a principal component analysis, dimensionality reduction, latent factor model applied to genetic sequence data from microorganisms, bacteria, I believe, that live in various places, in particular focusing on bacteria that live in different parts of the body. Like there's bacteria that are specialized to living in your mouth, and bacteria that are specialized to living in your gut and on your skin, and so on and so forth. And then there's, a bacteria that lives in aquatic environments or fossilized, and there's fossil records for this kind of stuff. And then most importantly, there are samples of bacteria that in this particular study were enriched with viruses. So when they ground it up into the DNA stuff, it was basically corrupted. We have intentional outliers here. And because MDS with the squared losses in PCA, basically PCA is very susceptible to outliers and does a bad job. If you then just switch over and do MDS with these robust distance functions, D1 and D2, you get a much nicer embedding, right? Yeah, cool. We'll talk about that in just a second, but there's some more stuff that you can do in to MDS models, right? In particular, MDS models still focus on large distances, regardless of the norms that you're looking at, right? And this, even though we just showed a success story, it leads to some crowding like PCA. So one early attempt to address this was called Salmons Mapping, and we bring this up because we use it to compare against modern methods. And it's really simple. It's just a weighted MDS, so that large and small distances are more comparable and you don't get overwhelmed by large distances because you just normalize by the distance between the x's. And remember, this is really straightforward, particularly when we start talking about automatic differentiation and deep learning, right? All we're doing is we're taking derivatives with respect to these Zi and Zij's, and we're trying to learn things that match distances in X and Z space, right? No big deal, okay? So here's, standard PCA, here's L1 normed MDS, and on the right is a weighted form of Salmons mapping applied to the same data. And I'll do this again later on in the lecture, but do remember that the point of all of this is is that when you look at this data originally, you will not actually have the labels for the data, right? You're going to get these genetic sequences and you're going to put them into some sort of clustering algorithm, you're going to put them into some dimensionality reduction algorithm, and you hope that the clusters that come out correspond to things that are scientifically meaningful or whatever, right? And the way you validate these kinds of techniques and look at them is to say, okay, do various, I guess the brown is stuff, are bacteria that live in your poo, right? So would you then run clustering on this dimensionality reduction? Okay, so again, all of the latent factor modeling stuff that we're talking about is useful for lots of different things. The principal use that we're looking at today is visualization, but at the same time, you should think about this as an unsupervised feature preprocessor, right? So if you take your x's and you want to do dimensionality reduction for whatever reason, because it's going to, clustering will work better in this space or whatever, then yes, you would run a clustering algorithm on this reduced dimension representation of the data. And it need not be a two-dimensional representation. The two-dimensional representation is really only for visualization, which is what we're talking about today. And the effects of these kinds of dimensionality reduction, latent factor model, NDS things are visible in 2 dimensions, and and intuitions can run then into higher dimensional embedding spaces. Good question.
I have a question. So if you make the mean of every row and every column of the data 0, like double centering, then I guess the MDS would be equivalent to PCA, right?
Mm-hmm. Okay. Yeah. That's basically what that Chris Williams paper did for the first time, or showed for the first time. Other questions? Comments? Concerns? I still have time to bomb the lecture, don't worry. All right, cool. Okay, so we really would like somehow to get at a representation of the data that actually reflects its actual axes of variation, a small number of dimensions or features, or loadings, or embedding space dimensions, or whatever, that describe the data well, ideally perfectly, right? If you, and we'll return to this in just a second. If you think about the example of the A images that live in a 700 and some odd dimensional space that we looked at the other day, where they were rotated and scaled, right? I said something about manifolds there, which I said that this entire data set and then this entire space of images, of rotated and scaled images, can be described by 2 numbers, right? It's just the rotation and scale. But if you think about where those numbers live in the 700 dimensional space, it's some weird planar surface that is somehow wrapped and folded inside of the 700 dimensional space, right? But if you have those 2 numbers, then you can cluster, you can classify, you can basically do anything you want to, because you have a complete map or are they called map? No, what are they called? Maps. Chart. You have a complete chart for the data. Okay, so yeah. So let's, with that example in mind, let's think about a data living in some high dimensional space. Here, high dimensional space is going to be 3, and we have a data manifold, a 2-dimensional data manifold that lives in this space. Okay, cool. The canonical learning pedagogical test example in machine learning is this Swiss roll data set. Okay, and just to be clear, right, the colors here mean nothing. They're just to help you see what's going on. And the point is that there is actually a way of indexing any point on this manifold. That was a terrible place to draw the quote unquote horizontal axis. The horizontal axis could be anything in this, in that direction that I just drew. And then a number that indexes along this direction, which is now curvilinear, but actually just 2 numbers will tell you where you live on this manifold, right? And it just completely describes this data set. You don't care about the 3-dimensional space, you just care about this 2-dimensional latent embedding, right? So the manifold is actually just directly addressable in this kind of a way, just 2 numbers, right? Where you are along the manifold, then one direction, where you are along the manifold in the other direction. So if you just use regular distances, right, in this particular case, and you can see why this is a good example, PCA nor NDS will discover a good latent variable representation or embedding for this data. Right, if you pick two principal axes of variation, it's very difficult to say what they'll be, but certainly there would be one in this direction, one in that direction, so to speak, right? And what's going to end up happening is you're just going to mash the data down onto that plane, and PCA is going to give you a representation that looks like what's shown here, right? And MDS is going to do the same thing because this point is as close to any of these points as it is to the, man, I shouldn't have drawn the red region. This point is as close to any of these points across as it is to something out here. So the folding or warping that would happen in MDS is not going to be able to actually lay this thing out flat because the distances are like matching distances in the original data. It doesn't account for the fact that really actually the distance from here to here requires you to go all around this way, right? In Euclidean space, you have this sort of shortcut path, and that's no good, right? The MDS is going to recognize that and try to match that, right? So the way to deal with this is to think in terms of geodesic distances, which are just basically distances along the surface of the manifold again. So the distance from this point to this point, is the shortest path on the manifold. Okay, fine. Okay, not across through Euclidean space. That's no fair. Okay, right. So again,
why do we need to go through the data plane?
Why do we need to go through the data plane? Okay, so I don't know what the data plane here is. I think, okay, all right. So let me deal with the first one first from Tianyi. Good question. So if you mean, why do we need to go through the manifold? The point which I tried to illustrate earlier is that if you think about MDS, right? And it's difficult to draw on here, but for this point, right? All of these points here are the same distance as this point, as a way, basically this distance and these distances to all these points out here are the same, which means that when you do metric dimensional, when you do MDS, multidimensional scaling, whatever Zs you learn will try to preserve all of these distances exactly, right? So it won't be able to actually unroll the roll and actually have a low dimensional representation. Basically, it won't be able to discover a good two-dimensional representation of this two-dimensional structure living in a three-dimensional space, because of the fact that it can't unroll it because it has to preserve all pairwise distances. Yeah, okay. In this example, we have a very clear manifold of data points. How often does our data actually look like this? That is a really good question. The answer is not, we don't know, right? But it's pretty clear. I would say what is clear is that data lives on some manifold in almost every natural data set that you can think of. I mean, images are the perfect case, right? Like natural images, it's impossible to describe the manifold, but we don't know how many dimensions you need to describe it, but you certainly don't describe it with a full 4K resolution, multi-million dimensional vector. That's in other words, images don't fill the entire image space, right? What do the colors represent? I said that the colors represent nothing other than to help you figure out where things are when we unroll it and plot it. Why do we need to unroll the data? What's an example of this? So the example was if you have, if these are, I'll do it over on this one, right? If this, at this very tail end, we have big A's, and at this little end, we have little A's, and on the other axis, we have little A's like this, and over here we have rotated A's like so, right? If we want to cluster together the little A's or divide between little A's and big A's, right? It's pretty easy to do in the geodesic, in the manifold. There's a dividing line right there. These are big, these are small, right? But if you try to do it in any other projection of the data, it's quite difficult, right? If you draw a line through here, these are big, these are small-ish, these are small, and these are, that line wasn't perfect, those would be big, right? So like, how do you divide the data? And so it's, yeah. Would MDS be able to handle self-intersecting or nearly self-intersecting manifolds as well? So MDS is not set up to deal with manifolds. That's not what we're talking about. So we're talking about ISOMAP right now. But we will run MDS as a subroutine inside of ISOMAP. Yeah. Can you give an example of how our data looks like this? I just did. That's this. So each one of these images lives in R to the 768 or whatever. Okay. But this entire space of images, this data set, really only needs two numbers to describe it, right? This way, which is some rotation, angle theta, and this way, which is some scale, you know, who knows, whatever, doesn't matter, lambda. Okay. We have no idea what this looks like in the 768 dimensional space or whatever. These images are, these points are going to be points in that space, right? But who knows where they're going to look like, right? But we know that this entire space is addressable directly because we can visualize it. We made it this way, right? Right. Okay. Fine. So Euclidean distance, I guess the point is that Euclidean distance in the 768 dimensional space is not. We already know that like that's not going to indicate well what. Yeah, it doesn't reflect a manifold structure. Like it's not. You know, the distances between things are going to be. Yeah, just not reflective of the inherent structure of the problem. So the geodesic distance here would be the distance through the space of rotations or sizes, okay? So ISOMAP is a pretty simple algorithm, really, where you start with your data set, and this is just some data set X, where now we're in 2 dimensions, and the manifold is a 1-dimensional manifold, which is just, you know, there, right? But we don't know that manifold, right? So we have to go find it, right? So how do we do it? Well, we have to find neighbors. How do we find neighbors? We'll talk about that, but it's, you know, you do some sort of k nearest neighbors type thing or epsilon ball search, right? Then we have to actually compute distances in the original Euclidean space, because we'll make the assumption that the space in which the data lives is locally linear or locally Euclidean. So we're going to compute distances for all of those and put a weight on those, right? Then, in order to compute pairwise distances, we're going to not compute distances like this. No. We're going to compute distances by the geodesics on this graph. In other words, walking over the graph. And we need to get all pairs shortest paths between all data points. Okay, Payman, computer science algorithm. What do you run to get all pairs shortest distances?
Dijkstra, probably.
Hey?
Dijkstra algorithm?
Dijkstra's algorithm, yeah. All right, the computer scientists finally have a use for Dijkstra's besides Google Maps, right? So yeah, so you run Dijkstra's algorithm. And then after you do that, then you run multi-dimensional scaling or MDS with these geodesic distances, right? So instead of Euclidean distances, you compute geodesic distances and then run MDS on that. and that returns you an embedding Z for every data point that reflects the distances or tries to maintain the distances. Yeah. In other words, just put it out there. There is no way, if you construct your neighbor graph correctly, there is no possible way to go from this point to this point except going through the manifold, right? So the distances that you get are different, right?
We're generating a mesh from the data and then doing MDS on the surface of the mesh?
On distances computed using shortest paths on the mesh. Yeah, that's correct. So instead of Euclidean distances, we're considering distances between nodes in the graph. That's right. And the nodes in the graph are the nodes in the graph locally have Euclidean distance, but globally have geodesic distance approximated in this case by Dijkstra's algorithm. Yeah. There are other more fancy ways of doing that, but because you can have curvilinear paths and there's all sorts of topology is nasty, and it's not my strength at all. So anyway, what's cool is that when you have a well delineated, and the comment section has already pointed this out, when you have a well delineated manifold, like there's not like shortcut connections and that sort of stuff, PCA will do the wrong thing, but isomap will totally kick butt, right? So in a proper Swiss roll setup and with the right hyperparameters, isomap just simply unrolls it and gives you the direct parameterization of the manifold. Okay, that's pretty cool. But people did, I forget, maybe it was Shaunach that asked this question, right? If you have data that's in here and your graph building algorithm it connects to these points, now you've got a problem, because now you've got shortcut paths, and that will lead to messes as well, right? So this is no one size fits all solution. There's no panacea, but it does something, right? It is sensitive to having the right graph and points off the manifold, and the gaps in the manifold cause problems. So sometimes you actually do have the graph though, just to be. What if we have some high dimensional data like a cone? How is isomap going to unroll it? Again, depending on let's assume, just for the fun of it, that we have the neighborhood graph, right? So we're going to have some neighborhood graph. This is the worst cone ever. That connects all of the neighbors and connects them in this direction, and that's it, right? Then what's going to happen is it's not super obvious how it's going to unroll it, but MDS is going to attempt to unroll this in a sensible way, right? And a sensible way to unroll it would be to have, in 2 dimensions, just a planar set of connections, like so. Recommender systems explain how you get stuck in a weird chain of videos on YouTube, but yeah, the point here is that in some cases you actually have the edges, the points that are connected together, but it's it's not, we already know some techniques for constructing such a graph, right? One is really obvious. You just construct an epsilon ball around every data point and connect all of its neighbors together that are within some threshold. That was like what we did in, I guess, DB scan density-based clustering. In approach number 2, we just do a k nearest neighbors graph and connect xi and xj, either if xj is a k nearest neighbor of xi, or vice versa, or and, right? And graphically, it's really obvious what's going on, right? There's the epsilon ball approach, which just adds an edge if you're below some threshold. Then there's k nearest neighbors, where you either look at or and relative to whether or not data points are k nearest neighbors of one another. The and, generally speaking, won't connect outlier points. The or will, and depending on the size of the epsilon ball, you'll leave some stuff disconnected out here as well, right? And you can ask, what are the distances that you compute for things not relying on the manifold? They're basically infinite, which means you can just do whatever you want with them. You pick some default large value, and you go from there. Okay. So that's ISOMAP. Basically, it's a latent factor model for visualizing data on manifolds, or trying to find the intrinsic dimensions of a data manifold living in higher dimensional space. And it works by finding the neighbors of each point using some sort of k nearest neighbors algorithm or an epsilon graph. You compute edge weights using a Euclidean distance in the original space, which is just usually a distance between the neighbors. The edge weights are, that is, and then you compute shortest path between all points. Almost always computed using Dijkstra, but there's other less efficient ways of doing it, or more exact depending on whether you want curve paths and that sort of stuff. Then you run some multidimensional scaling algorithm using those distances. And here's an example of another data manifold. These are black and white or grayscale images of hands that are either open and closed or rotated, and any combination thereof. So there's really only 2 axes of variation, right? Again, these are going to be very high dimensional. These spaces live in some big space, right? But really, you should be able to describe the entire space of images, even though they're grayscale, with just 2 numbers, which is how extended the fingers are and how much the wrist is rotated. And if you run PCA ISOMAP in this space, you will recover such a manifold, 2-dimensional manifold. Pretty cool. Cool. All right. So if we go back to IMNIS digits, images of IMNIS digits, your favorites, and we run PCA on them, we get something like this, where the reds are the zeros, the pluses are the ones, so on and so forth, right? If we do Salmons mapping, where we normalize the distances, we get a different kind of clustering behavior. And if we run ISOMAP, we get clusters that are much more well delineated, at least in 2-dimensional, in 2D. But you can argue that it doesn't really make sense that the intrinsic dimension of the digit manifold is 2-dimensional. So ISOMAP in 2 dimensions doesn't really make a huge amount of sense here, nor would PCA nor Salmons map. But we're thinking about like right now we're thinking about visualization, and we're thinking about projecting into low dimensions, very, very low dimensions. Okay, fine. That's one step. This is all kind of a setup, a bait and switch almost, to say there is another approach called t-SNE, which is kind of the modern state-of-the-art method for doing this kind of low-dimensional latent factor modeling. But before we talk about the particulars of t-SNE, and we only just talk about them just a teeny tiny little bit, it's pretty straightforward. You can look it up on Wikipedia. The point, which I said in words before, but I just want to drive home, is that when we're working with data like this, right, we do not start with the labels, right? We start with some data, and we run it through these algorithms, and we hope that we get some sort of clustering or grouping or projection or loading or so on and so forth, that's useful. Sorry, I missed Payman. You're slacking on the job. So are we able to reduce the risk rotation finger extension of a hand to 2 dimensions? Yes. So in this particular data set, which consists of only images of hands in this, and any combination in those in that space, yes, that defines a clean, nice manifold, which isomap can unroll and turn into 2 basically numbers that index that entire subspace of images, right? Cool. So yeah, we get this data, and what we hope is that after we do this kind of dimensionality reduction / latent factor modeling / whatever, that we can go into a Salmons map and say, I see a high density region over here. And then you go in and manually look at this or try to run some sort of clustering algorithm or whatever, and discover that in fact, there are ones out there in the data set that are similar in this kind of important way, or there are zeros, right? Isomap, same thing. Here, the ones are more well isolated. That's pretty cool. t-SNE really knocks it out of the park, right? So when you run MNIST through, you really get very clearly separated clusters. And again, for discovery purposes, you want to be able to go and look at these clusters and label them after the fact. Or if you're doing some sort of classification or something like that, clearly, however you decide to, whatever classifier you decide to use, right? It's going to divide up this space will be easier to classify in than the other 2. Okay, so there's a whole bunch of digits and their embeddings. Fine, we can just do this forever, right? Okay, fine. So what's t-SNE? The key, there's like one main idea in t-SNE, which is that instead of focusing on large distances or small distances or something like that, you focus on distances to neighbors, period, right? And you try to make all the neighbor distances actually consistent, but you allow large variance in other distances. So here's a silly data set, and we can imagine what PCA would do here. You try to find some axes of principal axes of projection, and you try to preserve the large distances, right? And this leads to crowding because you're not actually focusing on any of the small distances. That's basically principal components tries to find the axes of principal variation, which focuses on large distances. t-SNE tries to actually preserve neighbor distances explicitly, like all the neighbor distances. Preferentially over all pairs, if that makes any sense. So out of all pairs, you'd rather make sure that all neighbor distances are well preserved rather than distances over all pairs. Okay, and this allows it to basically find embeddings that repulse where there are actually gaps in distances. Okay, this is a tan slide. It's easy. You can look it up on Wikipedia. Basically, there are specific, non-trivial, and very actually interesting choices for D1, D2, or D3 that have probabilistic interpretations. It's kind of a cool model, actually. But basically, for D1, you use a Gaussian centered at each data point to compute the probability that each xij is a neighbor. And it's similar to basically a k-means algorithm weighted by closeness. You don't need an explicit graph. D2 does the same thing. You compute the probability that every other z is a neighbor, but you do it with a heavy tail distribution. So you're allowed to deviate for large distances, right? Or yeah, that's basically it. And then you compare distances between, you compare the distances in X and Z space using the KL divergence, which is basically an entropy-like measure. And that's it for t-SNE. So cool. If you take t-SNE and you run it on, say, for instance, Wikipedia articles about war represented in bag of words representation, you get identifiable clusters corresponding to different events. These are labeled with events afterwards, so that's pretty cool. if you're a large manufacturer of stuff and distributor and seller of stuff, Otto had a product classification challenge, 200,000 products, 90 features. They ran t-SNE on the 90 dimensional feature vectors. Otto apparently owns Crate and Barrel, if you're familiar with Crate and Barrel. So this is probably like, you know, a fancy wine glass or something like that. But basically there are general product categories that you can deduce from feature vectors. Cool. And this is a sort of an illustration of the kind of science win that you hope to have here. These are actually healthy bone marrow cells that genetic analyses are done on, and then t-SNE is applied. And the kind of thing that happens, and I'm not sure if it happened in this particular data set, but it has happened relatively regularly using this kind of thing, is they go in and they say, okay, well, we know what this kind of cell is. We know something about its genetic signature. We know what this kind of cell is, but actually we just did this broad assay. And now there are these other clusters here and we don't know what they are. They actually have found cell types by going in and doing this kind of t-SNE or other MDS-based latent factor learning plus visualization. It's cool. Okay, I'm running short on time, so I'm gonna not actually take questions here, even though the questions have been good, and instead just finish with a nice little thing that segues into deep learning nicely, which are, if we want to do latent factor, if we want to learn latent factor representation for words, how do we do it? So in everything we've talked about so far, the words are just represented by an index. Cat is word, 1,000, 100,000, 124,056, right? Out of a bag of words, all of your dictionary entries, a couple 100,000 in English, right? This is clearly not an efficient representation of words, right? Aren't cat and kitten kind of close, but if you just have like numbers that represent their dictionary entries, they're actually rather far apart. So this is kind of dumb, however you're going to use the data, right? So for many, many applications, including the deep learning applications we'll look at, or whatever, we do want latent factor representations of individual words, where closeness in the latent Z space should indicate some sort of similarity, and maybe even distances and directions in that latent space could represent meaning or changes in meaning.
It means if we penalize more for large loss, do we get t-SNE?
No, we can go through t-SNE in detail later if you want to, but in short, no. So yeah, so what we're going to talk about is word to vector very rapidly. We'll do a little bit more on Monday as well. But let's think about these phrases: the cat purred and the kitten purred, right? Or the black cat ran and the black kitten ran. Basically, the idea of latent factor models for words are that words that occur in the same context are very likely to have similar meanings, right? And this has been used all over the place. Word2Vec in particular uses this idea to design what's like an MDS-like distance function. So there's a couple of different approaches. We're going to talk about basically this one only, the continuous bag of words, where you try to predict a word from the surrounding words, okay? So you have words in the surround, you do something, and you try to predict the identity of the word in the middle, so to speak, okay? Cool. And the idea is we want to train latent factor to solve one of these supervised learning tasks, okay? So in Word2Vec, each word is represented by a latent vector in some high dimensional space, 200 dimensional space or whatever. And in continuous bag of words, we optimize the following likelihood, where we try to optimize the likelihood of the ith word, and we're going to the likelihood of all the joint likelihood of all the data is just the product of the individual probabilities of all the words given their surrounds. And we're going to make the IID assumption where we just define that probability to be the product of the conditional probability of generating a particular word xi given the surround word xj in the surround, right? And in particular, we're going to make an assumption about the distributional form of this conditional distribution, which is that it is a softmax distribution over all words, where the conditional probability of xi given xj is given by the inner product between the latent feature vectors or the embedding vectors for word I and j, summed over all words in the vocabulary to normalize that into a conditional probability. Right? So zi given zj is just the expression that we have there, and we apply gradient descent to the logarithm. This encourages the latent codes for similar words, i.e. similar words in the same context, to be close, and the inner product between latent features to be small for words that don't appear in the same context. That makes them far apart. The continuous bag of words denominator sums over all words. Other approaches are more complicated. They have to sum over larger spaces, and there are ways to speed that up, including in summing over all words. Although that's usually not too bad, where you can do negative sampling, where you just sample amongst the vocabulary. What's cool is if you then run an MDS visualization on the resulting feature vectors, what you get are embeddings that suggest that the distances between vectors might represent semantic relationships. So if you see here man, and there is a vector, and this is basically a visualization of the embedding space Z. Where if you move in this direction, you effectively change the gender tense, or however you say it in natural language processing terms, from king to queen and from brother to sister. And basically these vectors look about the same length, and they point in roughly the same direction. And the same story can be shown on the left. Okay, whoo, yeah. So MDS, cool. MDS is just some loss function. We're doing, non-parametric latent factor learning. We're taking derivatives with respect to the z's. You can stick in all kinds of different distance functions, losses, weights, so on and so forth, and you can get some pretty cool results for learning embeddings. Manifold learning focuses on learning low-dimensional curve structures in a higher dimensional host space. ISOMAP is one of the most common approaches. It's been cited something like 14,000 times, and it uses shortest paths and a weighted graph to approximate geodesic distances. t-SNE is a really cool and promising new MDS method, and Word2Vec is a way of learning latent factor models for words based on their context in a large corpus. And finally, on Monday, we will start what everybody took the course for. We will do 1 week on deep learning, which is approximately 2 lectures more than we need to explain what's going on in deep learning. So we'll spend a week having some fun talking about deep learning. So cool. Thank you very much for your time. Sorry for running late, very late as it turns out. Thanks for staying with me. Questions? As with most of the lectures in this course, because at the very beginning of the course we said, at this level for sure it's better to actually learn about a ton of different methods, and to be exposed to them so you can go off and learn about them on your own. All of the stuff that we're talking about here has much deeper stuff. There's, you can go as deep into the rabbit warren as you want in basically any of these things. And the principal concerns that you should keep in mind are that maybe we want a lower dimensional representation of the data because maybe it's good for discovery or visualization. Maybe we want a higher dimensional one for better classification with generic models. Maybe we want a lower dimensional one for, there's gradient descent, like the tools that you have, loss functions, so on and so forth. They're pretty powerful once you understand how to sort of work in this space. And that's really the important thing. What's the difference between data mining and machine learning? The course says data mining, but I don't recall hearing the phrase used once. Yeah. Okay. I have a hard time answering this question in a way that doesn't offend data mining people. We did touch data mining a little, sort of. It is much more of a machine learning course than it is a data mining course. Yeah, I'm just gonna say that. Yeah, I'm just gonna leave it alone. Actually, that one I'm not gonna answer because I'm just gonna get myself in trouble. And these lectures are recorded, so. Does Word2Vec, yeah, so the models that are considered in data mining, no, I'm not. Does Word2Vec use geodesic distances? No, it does not use geodesic distances at all. No, it just learns the Zs, and there's no notion of manifold there at all. It's just Word2Vec, and unfortunately, I would have said a little bit more about it. The transition. It's a nice way to transition into. It's a lasting transition into deep learning, and it's extremely widely used. So we have to get it in there, and it really is it's learning a latent embedding, so it falls more naturally into the latent factor modeling part of the course. All right. Say goodbye to Payman's smiling face.
Thanks for the lecture.
Thanks, everyone.